In chemistry, an ionic compound is a chemical compound in which ions are held together by electrostatic forces termed ionic bonding. The compound is neutral overall, but consists of positively charged ions called cations and negatively charged ions called anions. These can be simple ions such as the sodium and chloride in sodium chloride, or polyatomic species such as the ammonium and carbonate ions in ammonium carbonate. Individual ions within an ionic compound usually have multiple nearest neighbors, so are not considered to be part of molecules, but instead part of a continuous three-dimensional network, usually in a crystalline structure. Ionic compounds containing hydrogen ions are classified as acids, and those containing basic ions, hydroxide or oxide, are classified as bases. Ionic compounds without these ions are also known as salts and can be formed by acid-base reactions. Ionic compounds can also be produced from their constituent ions by evaporation of their solvent, precipitation, freezing, a solid-state reaction, or the electron transfer reaction of reactive metals with reactive nonmetals, such as halogen gases. Ionic compounds typically have high melting and boiling points, and are hard and brittle. History of discovery. The word ion is the Greek omikron nu, ion, going, the present participle of epsilon nu alpha iota, in a, to go. This term was introduced by English physicist and chemist Michael Faraday in 1834 for the then unknown species that goes from one electrode to the other through an aqueous medium. In 1913, the crystal structure of sodium chloride was determined by William Henry Bragg and William Lawrence Bragg. This revealed that there were 6 equidistant nearest neighbors for each atom, demonstrating that the constituents were not arranged in molecules or finite aggregates, but instead as a network with long-range crystalline order. Many other inorganic compounds were also found to have similar structural features. These compounds were soon described as being constituted of ions rather than neutral atoms. But proof of this hypothesis was not found until the mid-1920s, when X-ray reflection experiments were performed. Principal contributors to the development of a theoretical treatment of ionic crystal structures were Max Born, Fritz Haber, Alfred Landé, Erwin Madelung, Paul Peter Ewald, and Kazimierz Fagens. Born predicted crystal energies based on the assumption of ionic constituents, which showed good correspondence to thermochemical measurements, further supporting the assumption. Formation. Ionic compounds can be produced from their constituent ions by evaporation, precipitation, or freezing. Reactive metals such as the alkali metals can react directly with the highly electronegative halogen gases to form an ionic product. They can also be synthesized as the product of a high-temperature reaction between solids. If the ionic compound is soluble in a solvent, it can be obtained as a solid compound by evaporating the solvent from this electrolyte solution. As the solvent is evaporated, the ions do not go into the vapor, but stay in the remaining solution, and when they become sufficiently concentrated, nucleation occurs, and they crystallize into an ionic compound. This process occurs widely in nature, and is the means of formation of the evaporite minerals. Another method of recovering the compound from solution involves saturating a solution at high temperature and then reducing the solubility by reducing the temperature until the solution is supersaturated and the solid compound nucleates. Insoluble ionic compounds can be precipitated by mixing 2 solutions, one with the cation and one with the anion in it. Because all solutions are electrically neutral, the 2 solutions mixed must also contain counterions of the opposite charges. To ensure that these do not contaminate the precipitated ionic compound, it is important to ensure they do not also precipitate. If the 2 solutions have hydrogen ions and hydroxide ions as the counterions, They will react with one another in what is called an acid-base reaction or a neutralization reaction to form water. Alternately, the counterions can be chosen to ensure that even when combined into a single solution they will remain soluble as spectator ions. If the solvent is water in either the evaporation or precipitation method of formation. In many cases the ionic crystal formed also includes water of crystallization, so the product is known as a hydrate, and can have very different chemical properties. Molten salts will solidify on cooling to below their freezing point. This is sometimes used for the solid-state synthesis of complex ionic compounds from solid reactants, which are first melted together. In other cases the solid reactants do not need to be melted, but instead can react through a solid-state reaction route. In this method the reactants are repeatedly finely ground into a paste, and then heated to a temperature where the ions in neighboring reactants can diffuse together during the time the reactant mixture remains in the oven. Other synthetic routes use a solid precursor with the correct stoichiometric ratio of non-volatile ions, which is heated to drive off other species. In some reactions between highly reactive metals and highly electronegative halogen gases, or water, the atoms can be ionized by electron transfer, a process thermodynamically understood using the Born-Haber cycle. Bonding. Ions in ionic compounds are primarily held together by the electrostatic forces between the charge distribution of these bodies, and in particular the ionic bond resulting from the long-ranged Coulomb attraction between the net negative charge of the anions and net positive charge of the cations. There is also a small additional attractive force from van der Waals interactions which contributes only around 1 to 2% of the cohesive energy for small ions. When a pair of ions comes close enough for their outer electron shells to overlap, a short-range repulsive force occurs. Due to the Pauli exclusion principle, the balance between these forces leads to a potential energy well with a minimum energy when the nuclei are separated by a specific equilibrium distance. If the electronic structure of the two interacting bodies is affected by the presence of one another, covalent interactions also contribute to the overall energy of the compound formed. Ionic compounds are rarely purely ionic, i.e., held together only by electrostatic forces. The bonds between even the most electronegative, electropositive pairs such as those in cesium fluoride exhibit a small degree of covalency. Conversely, covalent bonds between unlike atoms often exhibit some charge separation and can be considered to have a partial ionic character. The circumstances under which a compound will have ionic or covalent character can typically be understood using HSAB theory, whereby the compounds with the most ionic character are those consisting of hard acids and hard bases. Small, highly charged ions with a high difference in electronegativities between the anion and cation. This difference in electronegativities means that the charge separation, and resulting dipole moment, is maintained even when the ions are in contact. Structure. Ions typically pack into extremely regular crystalline structures, in an arrangement that minimizes the lattice energy. The lattice energy is the summation of the interaction of all sites with all other sites. For unpolarizable spherical ions only the charges and distances are required to determine the electrostatic interaction energy. For any particular ideal crystal structure, all distances are geometrically related to the smallest internuclear distance. So for each possible crystal structure, the total electrostatic energy can be related to the electrostatic energy of unit charges at the nearest neighbor distance by a multiplicative constant called the Madelung constant that can be efficiently computed using an Abel sum. When a reasonable form is assumed for the additional repulsive energy, the total lattice energy can be modeled using the Born-Landé equation. Using an even simpler approximation of the ions as impenetrable hard spheres, the arrangement of anions in these systems are often related to close-packed arrangements of spheres. with the cations occupying tetrahedral or octahedral interstices. Depending on the stoichiometry of the ionic compound, and the coordination of cations and anions, a variety of structures are commonly observed, and theoretically rationalized by Pauling's rules. In some cases the anions take on a simple cubic packing, and the resulting common structures observed are some ionic liquids, particularly with mixtures of anions or cations, can be cooled rapidly enough that there is not enough time for crystal nucleation to occur, so an ionic glass is formed. Defects within an ionic crystal. There will usually be some point defects, but to maintain electron neutrality, these defects come in pairs. Frenkel defects consist of a cation vacancy paired with a cation interstitial and can be generated anywhere in the bulk of the crystal, occurring most commonly in compounds with a low coordination number and cations that are much smaller than the anions. Schottky defects consist of one vacancy of each type, and are generated at the surfaces of a crystal, occurring most commonly in compounds with a high coordination number and when the anions and cations are of similar size. If the cations have multiple possible oxidation states, then it is possible for cation vacancies to compensate for electron deficiencies on cation sites with higher oxidation numbers, resulting in a non-stoichiometric compound. Another non-stoichiometric possibility is the formation of an F-center, a free electron occupying an anion vacancy. When the compound has 3 or more ionic components, even more defect types are possible. All of these point defects can be generated via thermal vibrations and have an equilibrium concentration. Because they are energetically costly, but entropically beneficial, they occur in greater concentration at higher temperatures. Once generated, these pairs of defects can diffuse mostly independently of one another, by hopping between lattice sites. This defect mobility is the source of most transport phenomena within an ionic crystal, including diffusion and solid-state ionic conductivity. When vacancies collide with interstitials, they can recombine and annihilate one another. Similarly, vacancies are removed when they reach the surface of the crystal. Defects in the crystal structure generally expand the lattice parameters, reducing the overall density of the crystal. Defects also result in ions in distinctly different local environments, which causes them to experience a different crystal field symmetry, especially in the case of different cations exchanging lattice sites. This results in a different splitting of d electron orbitals, so that the optical absorption can change with defect concentration. Properties: acidity, basicity. Ionic compounds containing hydrogen ions are classified as acids, and those containing electropositive cations and basic anions, ions hydroxide or oxide, are classified as bases. Other ionic compounds are known as salts and can be formed by acid-base reactions. If the compound is the result of a reaction between a strong acid and a weak base, the result is an acidic salt. If it is the result of a reaction between a strong base and a weak acid, the result is a basic salt. If it is the result of a reaction between a strong acid and a strong base, the result is a neutral salt. Weak acids reacted with weak bases can produce ionic compounds with both the conjugate base ion and conjugate acid ion, such as ammonium acetate. Some ions are classed as amphoteric, being able to react with either an acid or a base. This is also true of some ionic compounds, typically oxides or hydroxides of less electropositive metals, such as zinc oxide, aluminium hydroxide, aluminium oxide and lead oxide. Melting and boiling points. Electrostatic forces between particles are strongest when the charges are high, and the distance between the nuclei of the ions is small. In such cases, they generally have very high melting and boiling points and a low vapor pressure. Trends in melting points can be even better explained when the structure and ionic size ratio is taken into account. Above their melting point, ionic solids melt and become molten salts. Chlorides show molecule-like structures in the liquid phase. Inorganic compounds with simple ions typically have small ions, and thus have high melting points, so are solids at room temperature. Some substances with larger ions, however, have a melting point below or near room temperature, and are termed ionic liquids. Ions in ionic liquids often have uneven charge distributions, or bulky substituents like hydrocarbon chains, which also play a role in determining the strength of the interactions and propensity to melt. Even when the local structure and bonding of an ionic solid is disrupted sufficiently to melt it, there are still strong long-range electrostatic forces of attraction holding the liquid together and preventing ions boiling to form a gas phase. This means that even room temperature ionic liquids have low vapor pressures, and require substantially higher temperatures to boil. Boiling points exhibit similar trends to melting points in terms of the size of ions and strength of other interactions. When vaporized, the ions are still not freed of one another. For example, in the vapor phase, sodium chloride exists as diatomic molecules. Brittleness. Most ionic compounds are very brittle. Once they reach the limit of their strength, they cannot deform malleably, because the strict alignment of positive and negative ions must be maintained. Instead, the material undergoes fracture via cleavage. As the temperature is elevated, a ductile, brittle transition occurs, and plastic flow becomes possible by the motion of dislocations. Compressibility. The compressibility of an ionic compound is strongly determined by its structure, and in particular the coordination number. For example, halides with the cesium chloride structure are less compressible than those with the sodium chloride structure, and less again than those with a coordination number of 4. Solubility. When ionic compounds dissolve, the individual ions dissociate and are solvated by the solvent and dispersed throughout the resulting solution. Because the ions are released into solution when dissolved, and can conduct charge, soluble ionic compounds are the most common class of strong electrolytes. The solubility is highest in polar solvents or ionic liquids, but tends to be low in nonpolar solvents. This is principally because the resulting ion-dipole interactions are significantly stronger than ion-induced dipole interactions, so the heat of solution is higher. When the oppositely charged ions in the solid ionic lattice are surrounded by the opposite pole of a polar molecule, the solid ions are pulled out of the lattice and into the liquid. If the solvation energy exceeds the lattice energy, the negative net enthalpy change of solution provides a thermodynamic drive to remove ions from their positions in the crystal and dissolve in the liquid. In addition, the entropy change of solution is usually positive for most solid solutes like ionic compounds, which means that their solubility increases when the temperature increases. There are some unusual ionic compounds such as cerium sulfate, where this entropy change is negative, due to extra order induced in the water upon solution, and the solubility decreases with temperature. Electrical conductivity. Although ionic compounds contain charged atoms or clusters, these materials do not typically conduct electricity to any significant extent where the substance is solid. In order to conduct, the charged particles must be mobile rather than stationary in a crystal lattice. This is achieved to some degree at high temperatures when the defect concentration increases. The ionic mobility and solid-state ionic conductivity is observed when the ionic compounds are dissolved in a liquid or are themselves melted into a liquid. They can conduct electricity because the ions become completely mobile. This conductivity gain upon dissolving or melting is sometimes used as a defining characteristic of ionic compounds. In some unusual ionic compounds, fast ion conductors, and ionic glasses, one or more of the ionic components has a significant mobility, allowing conductivity even while the material as a whole remains solid. This is often highly temperature dependent, and may be the result of either a phase change or a high defect concentration. These materials are used in all solid-state supercapacitors, batteries, and fuel cells, and in various kinds of chemical senses. Color. The color of an ionic compound is often different to the color of an aqueous solution containing the constituent ions, or the hydrated form of the same compound. The anions in compounds with bonds with the most ionic character tend to be colorless. In compounds with less ionic character, their color deepens through yellow, orange, red and black. The absorption band of simple cations shift toward shorter wavelength when they are involved in more covalent interactions. This occurs during hydration of metal ions. So colorless anhydrous ionic compounds with an anion absorbing in the infrared can become colorful in solution.